Alrighty, folks. So, picking up where we left off last lecture. I think we finished up talking about the definition of a mineral and reminded you that there's four aspects to it. I don't do a whole lot of partial credit questions. We talked about that with the last test review, how if there was multiple answers, it was still only worth 1 point, so on and so forth. But that one is a definition that you're writing out, and it'll be worth 4 points since there's four things that I'm looking for. All right. So that one, is partial credit. It's for your benefit, really, instead of all right or all wrong. But what really sucks for you is if you write in the old a mineral is composed of one or more elements, and I give you a -4, because I've told you at least 5 times, don't write a mineral is composed of one or more elements for the definition of a mineral. So, moving right along. Yeah, not that fast though. All right. In lab, we talk about mineral groups. All right. It's classification. It's putting things in folders, boxes, whatever you want to call it. Groups. Okay, grouping them. Obviously, that's the name, grouping it. There's a number of ways to do this, and it really depends on your need. Okay, your field of work, your field of study. What are some you might know that we don't use? Gemstones. Okay, gemstones is a grouping of minerals. Ores. Ores is another one. Ores is for stuff that we mine, typically. All right. And while those are helpful and kind of descriptive, we use in here something much more low level, much more fundamental. All right. We classify minerals based on their composition, their chemical formulas. And the reason is that we're trying to reflect the importance of the underlying chemical structure that we just came off of the definition, remember, telling you that that must remain constant, and that's why the properties are always constant. And just to touch back on the properties for a second, I know you're all writing down this list, but if those properties that you rely on in lab to identify the specimens, if they weren't constant, all right, because the chemistry wasn't constant, then you wouldn't be able to do that task. And while many of you might think that's a good thing, I'm sure they would have found another way around it, so on and so forth. But it's because of this chemistry that we can do what we do. So we use groups that reflect that. You've heard me say the word silicates 100 times already. You'll hear it 100 more. We've got a group called the carbonates, the elementals. We've talked about that one a little bit. The halides, sulfurs, and the oxides. And we'll talk, what each of these means in turn. Eventually. We're going to focus, as I said, on one group in lecture. And that focus does a couple things. One, it's the thing you're going to see most frequently in lab, in the world around you, the silicates. Secondly, you might recall me talking a little bit about crystal structure, crystallography in lab as well. We're going to honor the importance of that by going sort of in depth into one of the groups. It's crystallography. It's not till the end of this lecture that we do that. But we'll talk about a number of different ways that you could construct silicate minerals. For right now, though, we'll just kind of keep it straightforward. You already know that this is the most common mineral group at this face of the earth. You'll hear me say surface of the earth. I should probably be saying at the crust of the earth. Yeah, question.
Whenever you can you hold out website?
What's there? You'll see all those again, but sure. You get it? Yeah. All right. And also, we wouldn't be able to talk about the composition of the silicates, structure of the silicates, if we didn't know what they were made out of. So we got SiO4. What's Si?
Silicon.
Silicon. Good. All right. Now, there's a couple different things. There's silicon, silica, and silicates, or kets. Silicates. Depends how you pronounce it. It's a tomato kind of thing. And I'm not going to make a tricky question about it or anything like that, which one is which, but do try to keep them straight. Silicon is the element. Silica is the compound. And silicates, kits, is the group. Okay? So this is silica. So silicon plus, what's the O? Somebody else. Oxygen. Good. How many silicons? One. How many oxygens? Beautiful. We know how to read chemical formulas. It's about as intense as it gets in here. Okay? So 4 oxygens surrounding a silicon. They happen to be in what we call a tetrahedral arrangement, tetrahedron. I use pyramid, okay? And at one point I'll be drawing triangles up there because there's little need to go into 3 dimensions. A tetrahedron is not they're not exactly the same. The way we look at the tetrahedron is sort of a triangle, a pyramid up on one of its ends. Not a corner, but on one of its ends. Not flat as gravity would hold it. You'll see it eventually. Next slide, probably. So a tetrahedron, but like I said, you'll hear me refer to them as pyramidal in shape. That's because of gravity. And like I said, I'll sometimes even draw it with triangles. So we've got the silicon-oxygen tetrahedron. We've got a new runner here for the longest vocabulary word of the semester so far, at least letter-wise. All right, silicon-oxygen tetrahedron. Now, this is what I meant about gravity getting in the way of things, and this isn't really a pyramid. The best way we could approximate this shape is for you to picture like your debit card or something like that, and you're holding the bottom of it with 2 fingers, your pointer and your thumb. You hold the top with 2 fingers, and you twist at the top so that the 2 top corners are facing perpendicular to the 2 bottom corners now, no longer parallel. That twisted shape is what we're trying to represent here on the board. All right. Again, not something that everyone can visualize. And I'm going to be talking about pool balls in a moment. And of course, pool balls are affected by gravity. So what would happen is this tetrahedron would fall forward. That front ball there, top center, would literally be, come forward into the classroom if you would. Be lying flat on the surface with 3 balls on the bottom, leaving 1 ball on the top, which gives you that pyramid. Now, if you can't picture that, again, just picture 3 pool balls. Make a little triangle with 3 balls on a pool table. Put a 4th ball on top. Of course, in reality, those bottom balls would roll out, but this is in our brains. We can do whatever we want in our brains. Those 4 balls represent what in the formula or in the equation? The formula, I should say. Well, of oxygens, yeah. All right, so those 4 are the oxygens, which means that one pink one in the center must be our silicon. All right, so let's mentally remove that 4th pool ball from our little pyramid and stick one of those little super ball bouncy things that you used to like when you were kids. Let's put that right in the middle, or a gumball even, okay? Not a big jawbreaker, but one of the little guys. And then put that pool ball back on top. So that silicon is completely covered by those oxygens then. What did I say? I've been teaching 24 years. That was here. I've taught a handful of years before that. For, let's say, 27 years, I've been meaning to glue 3 racquetballs together. So I can show this. Partially, I can't find my racquetballs anymore. I'm beginning to think my wife threw them away many moons ago. But you get the idea. And I think I do a pretty good description of it. If not, feel free to arrange some balls at home to help you understand this better. All right, so we are going to go into the other groups now. I thought it would become a little later. So that's it for the silicates for now. As I said, we'll delve a little deeper at the end of this conversation. The next group is the carbonates, so-called because they contain carbon. I didn't exactly point it out. I might have thought it was obvious a moment ago. But we call that group the silicates because it contains silica. Okay. So the carbonates contain carbon and Et. What's the Et? Oxygen, typically. These are your CO3. You know, you're going to see CO3 with some frequency. CaCO3, calcite, is almost everywhere. Absolutely almost everywhere. We talk about the silicates being the largest group at the surface of the Earth. And I'm sure that's true because I believe, you know, what these people tell me and all that. But calcite is the main ingredient in limestone, right? Limestone is everywhere on this planet. Absolutely everywhere. Anywhere that there's been an ocean, limestones are made in oceans. Anywhere that there's been an ocean, there's limestone. And at this point in the Earth's history, oceans have been just about everywhere. And yes, if you're wondering, yes, even in New York State, that is why we have limestone. They were in Ohio. There were oceans pretty much everywhere at some point. So calcite, the carbonates, while maybe not anywhere near as diverse as the silicates, is huge. Absolutely huge. There's another mineral that is fairly common. We don't see it in lab. It's called dolomite. And if I remember, it is a magnesium carbonate. And dolomite's an odd duck as well. They, I haven't looked too recently about it, but they first of all think maybe it only forms in cold water. We told you that limestone forms in the oceans. They're thinking that maybe dolomite only forms in cold water and possibly isn't even forming anymore. So don't quote me on that one, but if you actually care, you know, Google it and see if they've changed their minds about dolomite. But it's a little different structure than magnesium. A lot of you guys know limestone bubbles, calcite bubbles, right, with the hydrochloric acid. We didn't play with that in mineral lab, but we'll whip out some acid in sedimentary rocks. Okay, and the dolomite is. Was that a clapping applause? Yeah, it's fun. It is fun. But the dolomite doesn't quite work that way. Kind of like how marble is kind of really hard to get marble fizzing too. So you don't see a whole lot of carbonates in lab, but they are all over the place. The elementals. We talked about the elementals the other day when I was introducing the concept of compounds and not compounds. The idea behind an elemental is that there's just a single ingredient, and we call it a mineral. And there's sort of a running joke, although you know you don't really get it because it goes semester to semester, and typically you guys only see me once. But what's the difference between an element and a mineral, or in some cases a mineral and a rock? We're gonna pound into your head that halite, not an elemental, mind you, but halite or halite as a mineral, and then you're going to get rock salt. And you're going to tell you that rock salt's composed of sodium chloride. You're like, well, what's the difference? And I say, well, how big of a hunk it is. And that's sort of the same idea here. All right, when does it stop being an element and become a mineral? Well, when you got a big enough hunk of it in your hand. I guess we call it a mineral then. There is no line, okay, to cross. But these are minerals that are composed of a single element. So yes, arguably you're holding a bunch of elements in your hand. But that sounds weird, right? So we say we're holding a mineral. Sulfur, copper, graphite are a few you've come across or will come across in lab. There are others. There are others. And one of the big questions, you guys love to play Stump the Chump with me. You find out that graphite isn't lead and it's actually carbon, and you remember that diamonds are carbon, and you're like, wait, this is nothing like that. Yeah, it's that whole crystal structure thing, and I can't really describe it much more than that. Mineralogy is far from my field of study, and I know there's reasons. And if I read the reasons, I'd probably understand them. But you see that a lot, okay? You got one thing. And even the graphite, okay? Sometimes it's going to be as soft as the stuff you guys have in lab, and then sometimes it's significantly harder. They're like, wait a minute, what about the hardness test? Well, there's probably a subcategory, a subname on the graphites and so on and so forth. That if you were doing a much more involved list of minerals, it would show up in that manner. So, all right, anywho, so elementals, single ingredient. The halides. The halides consist of minerals that contain elements from the halide group of the periodic table. Well, that's helpful. So you remember the noble gases way down at the end? All right, well, the column before that is the halide group. Okay? Still not helpful, I know. Basically, it's a whole bunch of elements that end in ene, I-N-E. All right? Bromine, chlorine, fluorine, iodine, well, iodine, but you know what I mean. And what it boils down to is that you guys are sitting there trying to classify a mineral, and you can't find it anywhere. Like, this doesn't have silicon in it, this doesn't have carbons in it, more than one ingredient. I don't know what the hell it is. And someone in the group will say, wait, what was that weird one he said we had to look at the periodic table for? All right. So you'll see, like I said, you'll see fluorine in there, you'll see iodine, you won't really see iodine, but you'll see a handful of things from there. And again, for those that are into the chemistry, there is a reason enough that those are grouped together as their own thing. It's probably a reaction series kind of level thing. So, so the halide group. All right, the halide group. Oh, there's a couple examples. Yep, they went quickly. So you have the chlorine here, the fluorine here. That's not fluoride, it's fluorine. The sulfur group. So I went on and on a little while ago about we don't like these groups that just lump a whole bunch of stuff together. The ores. All right. Gemstones. You could see, just going through what we've done so far, how those groupings could be problematic. Some gemstones are just pretty quartz. Some gemstones are diamonds, and they're significantly different in their origins. Things that we dig up, ores, right? We dig up iron. We dig up salt. Again, significantly different. So we don't like those, with one exception, the sulfur group. And it's not just me who uses it for you guys with Geology 101, Geology 100, okay? It's a lot of different intro features. what it boils down to is that there are other groups. There's sulfites, there's sulfates, okay? And what that boils down to is how many oxygens are in the formula. And I don't even remember at this point which one is, SO4s and SO3s. CaSO4 is one of your minerals you're going to see. I believe that's gypsum. We got too much going on right now. You guys have too much going on to worry about how many oxygens are in the formula of one of the things. Okay, if you ever go on and take a mineralogy class, God bless, you'll learn this. Right now, we just say it's sulfur group. I'm happy that you remember a big old capital S is sulfur. All right? Not setting a bar or anything here. I'm just saying you got a lot on your plates. So, use sulfur group. Appreciate sulfur group. Okay, you got FES, CNS, PBS, CaSO4. That's really probably the only one that's not in its own little group there. There's one glaring exception, and this guy trips you up enough, and it still would be an issue even if we did use sulfates and sulfites. Where do you put sulfur?
At the beginning of the chemical equation.
Well, no. The mineral sulfur.
Oh.
Got a vote for elemental? Anybody else?
Is it
Okay.
all of the above?
So there's sort of a little rule here. There's a couple of these where you're going to wonder where to put it. And elemental always wins. Okay. I used to say elemental trumps all the other ones, and that was like a playing card reference, but now it's another reference. So at any rate, elemental always wins. So yes, sulfur is an elemental. Okay. You're going to see copper, okay, in your collection at some point. Copper arguably is an elemental, but many of your coppers have oxidation on them. We haven't done the oxides yet. They're next. But you're going to be like, oh, it's oxidized. What is it? 95% of that thing is solid copper. Don't worry about the fact that it rusted, oxidized. It's an elemental, okay? So sulfur, and I hate marking it wrong, but because I give 5 minutes here on it in class all the time, when it comes to the test, if you call sulfur a sulfur group, I got to put an X over it. So don't do that. There's the oxides. So by definition, to oxidize something is to add oxygen into the formula, right? There's a heck of a lot of oxygen in those formulas. How are you to know whether or not it was there in the first place or if it was due to exposure to air or water? Gosh golly, you're not, okay? What it boils down to is that first and foremost, we want to look at and make sure it's a hunk of metal, and then assume that that metal will oxidize, will rust. And just a reminder, rusting is only one type of oxidation, okay? Tarnishing, if you're familiar, if you or maybe your grandmother or great-grandmother has some silver around the house. Okay, silver tarnishes. You're supposed to tarnish or polish your silver. That's an oxidation. The Statue of Liberty, the fact that she was green for a long time, possibly green again. Copper goes to this green when it oxidizes. So rust is really only that thing that iron does, and that goes to red. Okay, but we do sort of use them. I use them more freely, interchangeably than I should. So one example of an oxide that you will see is iron ore. Okay, there are others. So I kind of went rogue a couple minutes ago, got ahead of my slides, and I started talking about artificial groupings. Okay, generally speaking, we don't use them in here. They're too generic. One example, or one exception to that, of course, is the sulfur group. The sulfur group. So yeah, I mean, generally speaking, gemstones are just fine. You're sitting there having a conversation. You even go to a rock and mineral show, you'll probably see gemstones thrown around a lot as a term. But, it's not horribly helpful because anything that's pretty and shiny arguably could go into that group. Already talked about, well, I didn't name it, but amethyst is a big one. I love amethyst. Okay, I'm not dissing amethyst in any way, shape, or form. It's just purple quartz, though. Okay, don't ever pay a whole lot for amethyst. It is quartz. Very cool color, but it shouldn't be online with necessarily some of the other, price-wise, some of the other gemstones that are out there. And Herkimer diamonds, you guys know, those aren't diamonds, right? They're quartz. Now they happen to be double-sided and have these cool little inclusions and maybe quite possibly are magical, but again, not diamonds. What else? Ores. We talked about the fact that salt is mined. All right. What group is salt in?
Hayroids.
Yeah, halide group. Okay. It is dug up, but that's merely, incidental in this point. Coal is mined. What group is coal in?
Carbonates?
Yeah, trick question. Coal's a rock. But yeah, it would be in carbonates. I agree with you guys. But no, coal is organic, therefore it's not a mineral. Trick question. All right, so you get the idea. But sulfur groups we really like because it helps us. And this is also, again, why I've told you a couple reasons why I don't really want you to go out. I don't endorse you going to Barnes & Noble's and buying a My First Rockin' Mineral book. Okay, I talked about it before because of the pretty pictures they put in there. You don't see pretty pictures in class. All right, I had a group the other day. I don't remember which group it was, but they were looking at a hunk of garnet and just, I could see it in their eyes that they really didn't believe it was garnet because it just looked so ugly. All right, and you're so used to seeing very pretty garnets because you see it in a ring or a, whatever, pendant. We don't get that stuff. So that was one reason why I said, please don't go out and buy a book or go to the Smithsonian's website to study for the test. All right. The other reason is because they do toss around these groupings, and sometimes they get more in depth than we do. Sometimes they're less in depth, and we want you to remember the ones that are on here. Because just a reminder, when it comes to the mineral test for geology folks, earth science, you don't have a rock or mineral test, lucky you. But with minerals, the group is half the test, okay? You can say that's sulfur, it's an elemental, that's rose quartz, it's a silicate. That's half the test. So you can't screw that up because you went and got a book to try and do better. Question?
Is a lab-grown diamond a diamond?
It's a great question. I had the conversation with my buddy about, he was a jeweler, and he would be getting these lab-grown sapphires. It was a big thing at the time for sapphires. Naturally occurring and inorganic.
So it's not naturally occurring.
But it's a sapphire and it's a diamond. So yeah, it falls out of this class conversation basically. Yeah, it's a good question. Is a clone a human? Dolly the sheep's clone, is she a sheep? Well, she's arguably a sheep, but is she Dolly? So on and so forth. But so yeah, we've got the skills now, and a lot of the problems with that artificial stuff is actually it's too perfect.
Are twins clones?
Oh, there you go. There you go. They have different names, so they're at least from that we keep them separated. But
Too much philosophy for quarter after 10 in the morning.
Besides, not all
that's
not all
late.
twins are identical, so let's kind of like simple water.
What's inevitable?
I said not all twins are identical.
Oh, identical. Okay. That's true too. That's true too. So, all right. But yeah, every so often we get to philosophize in here. There's nothing wrong with that. But yeah, I don't know. So I think they'd sell you if you go to a jeweler. They'll tell you it isn't a gem. It's a perfect gem. If you ask a mineralogist, They'll probably say exactly what I did. Well, you know. Okay, so that is it for this PowerPoint. The silicate one, I must have grabbed the wrong one because it should come next, but I guess that means it's in the in a different PowerPoint. So we've still got to talk about silicates. Good day. All right, folks, and we're back. This is not the PowerPoint I was looking for, but it has what we need. So we're going to utilize it. Do me a favor and check to make sure, and I'm talking to folks on campus and online here, that the PowerPoint that's posted has this stuff about silicates that I'm going to be adding. Actually, you print them out usually, don't you, Gary? Do you have this? Do you have this? You print these out usually, right? Do you have the silicates one? Does it go into the silicate structures? Or did the handout end with the last slide? Anybody else have it?
Yes, it does. Shape structures, framework structures.
Okay. And what were you saying, Maya? I didn't hear you. It does. Okay, good. All right, so I don't know where the hell that PowerPoint went. But this has the same content, so we'll catch up there. All right, so as I said, now we're going to go a bit more in depth into the silicates, okay? If you don't remember already, it's just narrative. Please don't copy it all down. Just reminding you that silicates are the most common group at the surface. While there are many other things in there, okay, only your quartzes, of course, are just silicon and oxygen. They should, okay, kind of focus on these guys for the rest of their ingredients. Why? Well, because remember that list of 8 most commonly occurring things in the Earth's crust? Silicon and oxygen were the top 2. These are the remaining 6. You don't need to write them down. You already got them in your notes somewhere. So one would think that these would be the most commonly bonding elements as well. This last day of lab, as we start week 3 of minerals on campus here, you guys, it's mixed into just two at home. You're going to be paying a lot of attention to those formulas because that's what you're going to use to assign the mineral groups. So just keep this in the back of your head that you should be seeing this stuff and see if that comes true. All right, we already told you that the silicate structure, I'm just going to skip through some of this stuff again because it's not the proper thing. 4 oxygen molecules surrounding a single silicon in this tetrahedral pattern. We showed you this. All right, here's the new stuff. So there are 4 ways that we can arrange those tetrahedra, okay? Or as we say, 4 main silicate structures. Isolated, chain, sheet, and framework. Isolated structure, chain structure, sheet structure, and framework structure. You will see each of these words again, so don't fret if I change the slide here in a moment before you've copied all 4 of them down. All right, isolated usually makes a little more sense in retrospect, but it is the most simple, so we start with it. But if you don't quite get it, wait until we get to some of the others, and then you'll be like, oh, okay. Or maybe you'll get it now. So, the rest of these are going to be bonded together. The tetrahedra are going to be bonded together at the oxygen to oxygen. And what do you guys remember, if anything, about oxygen bonds? Ooh, yeah, big word, big word. Even something simpler. Are they good bonds? Are they bad bonds?
Is there a weak bond or something?
Quite the opposite. They're supposed to be quite strong in this case. All right. So your oxygen bonds are oxygen to oxygen, strong bonds. These, the isolated structures, don't have that oxygen bonding. And that is what makes them isolated. So I'm going to tell you in a moment here. Olivine, garnet, and topaz. We didn't see topaz. Garnet's not a great example, but dang it all, we all had olivine in our hands. And when you drag that nail across the olivine, what happened? Yeah, it crumbled. You got a handful of green sand, right? And I said, okay, olivine tests way softer than it is. You drag that nail across it, it crumbled in your hand, you said, oh my gosh, this is soft. No. What you're actually supposed to test the hardness of was one of those tiny little green grains of sand, which is way too small to actually do. All you really tested was how well they were bonded to one another, which ain't great. All right. I don't jokingly say, but I sort of low-level science say they're held together by little more than static electricity, okay? It isn't static electricity, but that's something you're familiar with. You know, you rub a balloon on your hair and you stick it on your sweater and it's there. It's that level of charge. Garnet, like I said, it doesn't really act that way, but that is what they say, okay? You guys had a piece of garnet in your hand that was arguably many tetrahedra, but it comes off as a lot more solid. And again, topaz we just don't work with. So this is what I meant with triangles. I mean, it's sort of three-dimensional. Depends how you see things. All right. But so this is what we're going to be doing here, and we're going to start to string these together. In this example, what do we have at the corners? What do these corners, 4 corners of your tetrahedron or your pyramid represent? The oxygens, yeah, okay. So those are our 4 oxygens. So in the next slide, once we start putting them together, when you see 2 corners of the pyramids together, that's your oxygen bond. That's your oxygen to oxygen bond. All right, so isolated structures are just that. You've got it. We're not trying to say that there's just one tetrahedra there. There's many. They're just not bonded together very strong. So single chain. Single chain silicates. On the previous slide, yeah, it did just say chain silicates. There's 2 types. There's subcategory here, single chain and double chain. With the chain silicates, we're looking at literally just like if you had strung some paper clips together. All right, and you're bonding them. Let's get to the little picture here. Where's my little pictures? There's my pictures. All right, so the single chain, all right, just ding, da ding, da ding, da ding. And we move to the double chain. Well, we're basically bonding 2 chains together. And you might be thinking about, well, okay, what's the difference between that? If we put 2 of these, do they automatically bond? No. I know it isn't a super fresh image in your head, but what we're looking at here is hornblende and augite, okay? 9 and 10 in your specimen kit. And one was the long needle-like toothpicks. This is going to be a lot fresher for yesterday's lab than it is for last Wednesday's, folks. All right? But go back. Wednesday lab, you're meeting tomorrow. Go back and check out hornblende and augite. Sorry, I apologize. And hornblende obviously isn't just one long crystal. There's many long crystals. The idea is that they're just not bonded together side to side very well. And we lose that toothpicky, that needle-like structure when we move on to the augite because they're twice as wide. And, again, crystallography speaking, for whatever reason that doesn't make double-wide toothpicks. All right, it actually blurs the structure. Every so often in a piece of augite, you'll see some very nice crystal structure, but not very frequently, especially with the stuff we've got. there's cleavage issues, which again we don't focus on, but that's yet another reason why. Okay, I had to tell you guys, hey, look for the blackish green one, or hey, look for the black toothpicky one. Okay, because the stuff that's on the paper in the lab book, short of that, is sort of beyond Geology 101, discerning levels. And that's also possibly another reason why the the augite has such nice stair-steppy sort of. I'm sorry, the hornblende has nice stair-steppy sort of appearance to it. Okay, next is the sheet silicate. And sheet silicates, I want you to think micas. All right? There's another one which you'll recognize in a moment, but think of the micas, the muscovite, the biotite. And all they've done in this case is go beyond double chain to triple, quadruple, quintuple, so on and so forth. Don't do it with the nice big chunks that I put in the boxes for you guys to look at, but go over to the trays and find some of the thin sheets. All right? And you could literally take one of those pieces of mica and squeeze it between your fingertips, and it should bow like a playing card would. Okay? Really strong. Again, those oxygen bonds are amazing. So horizontally, that sucker sticks together. Great. But the layers themselves, all right, they flake apart.
They get everywhere.
Yeah, they do get everywhere, and they flake apart very easily. And that is that same sort of bonding that we see with the isolateds, back with the olivine. You didn't have to drag a nail across that olivine. You could rub it with your thumb and get those pieces of sand off. All right. So we see that bonding horizontally, layer to layer, but it's very strong going across. So that's why it's the sheet. Okay, they're sheets. So the other one was talc, all right? And the reason you don't necessarily see it in the talc is so soft. And you guys are always rubbing it because it is so smooth and talcy that you kind of just blur those cleavage lines right out of existence, let alone ever have a chance to peel it apart. And serpentine. When I was in Maryland, that was a big mineral there. It's kind of cool looking. But we don't have it in our collections. This PowerPoint is that old that I think I just put it in there because, hey, you guys have this in your state kind of thing. So, but talc and micas. And I don't care if you say talc or talc. Don't say talc. A lot of people call it talc. Last but not least, we got the frameworks. So you take that sheet structure, and instead of just these guys bond all the way across here, you've only got one oxygen left. And it's the tops of these pyramids, right? So now we're getting rid of that little static bond between the layers and replacing that with an honest-to-goodness bond. And we get some of our most... This is a real high-tech animation here. See that? It's supposed to be lined up. Sort of is. The way I explain it is picture the bottom. Remember we started with 3 pool balls, right? So that dimple that's on the top where you stuck your little gumball, well, you've got a little dimple in the bottom. So now we're taking the top of the pyramid on the bottom and attaching it up there into those oxygens above it. When you read your textbook, and by the way, for you textbook readers out there, we're actually in a lecture that's in an entire chapter for once. I'm not spanning 2, 3, or 4 chapters with it. You could read the mineral chapter, okay? I recommend it. So when you're reading in your textbook about these guys, they're going to talk about accessory minerals. Again, I'm keeping it a little simpler, a little lower level, and just saying that the oxygens are bonding. There's other stuff going on, okay? It's not at the level we test at anyhow, but it just keeps it simple as we're sort of building steps here, building frameworks up. So these guys, as you might have suspected, are some of the most durable minerals that you've got in your box. Okay? Again, I don't know a whole heck of a lot about mineralogy, but to me it makes sense because you've bonded every possible aspect of one tetrahedron to the other one. It should build a bigger, stronger thing. Okay? And as such, you see the quartzes and the feldspars. On top of that, we told you that the minerals, silicates, were the largest mineral group at the surface of the Earth. Of the silicates, nearly 3/4 of them are these frameworks. And again, to me, it makes sense because these are the most durable things. They're going to last the longest as well. So when we see them show up over and over and over again, and you're going to see these guys as we transition into igneous rocks very soon, you're going to see quartzes and feldspars. Sure, there's a little bit of mica in there. Sure, there's a little bit of hornblende, this, that, or the other thing. But quartz and feldspar, oh my gosh, over and over and over and over. So I'm sure there's some chemistry reasons, perhaps, why these guys form as frequently as well. But if you look at it from a 4.5 billion year perspective to what we have left now, only the strong survive kind of mantra. I would think these build up and throw that ratio if there ever was an even ratio. Okay. These just have longer sustaining. So, all right. So that was our in-depth look at the silicates. Sorry I had to switch PowerPoints there in the middle. Those of you that have the one that's on the class site out, is there anything that I didn't cover because we had to switch slides in the middle? I'm pretty sure this is everything, but you know how my brain is. You're learning how my brain is. All right, yeah, I do think we're good to go on that one. So, speaking of reading the book, all right, it's time for my disclaimer. I was one of those people who, I won't say I didn't go to class a whole lot, but my way of studying wasn't using my notes. It was opening up the book the night before the class and trying to read all the chapters that were on the test the next day, which, if you may or may not know, doesn't really work, at least for most people. Well, it really doesn't work for this class because as you're reading the minerals chapter, you're going to come across a handful of things that we didn't study, or we didn't talk about, I should say. They will not be on the test because we didn't talk about them. You will also not find some stuff that I did talk about, perhaps, or at least more in depth. And if that's the case, I'm going to test to what we talk about in here. So on the very first day when we were prepping for tests, or talking about how the semester runs, and I said when it comes time to prep for the test, use your PowerPoints, use your notes, okay? Because that's the stuff that I've distilled out of the minerals chapter for you. I do want you to read the chapter. Don't get me wrong, please, okay? But if you see stuff that we haven't talked about, don't stress about it. Oh my God, did I fade out? And you might have faded out and missed that, but that's where you check the PowerPoint. Say, nope, he didn't talk about that. Okay, I'm not going to worry about it for the test. If it interests you, if you have some questions about it, by all means, ask me, okay? But as far as testing goes, when it comes to reading the chapter, if I didn't talk about it, it's not going to be on the test, okay? Okay.
You really haven't said a heck of a lot, though, about this will be on the test, this PowerPoint.
Ah! Very observant. Definition of a mineral, of course. Of course. Silicate structures. What makes a mineral group the mineral group. Almost because it's all on this is such, when you see the minerals chapter, you'll see what I'm saying. This is such a bare bones lecture to begin with. So almost, I don't mean to sound self-important or whatever, but almost every slide on there is quite possibly, testable. With a few that are obviously narrative Okay. What's the most commonly occurring mineral group at the surface of the Earth? Okay, you saw that 17 times. So, yeah, stuff like that. And let us not forget that this first test, at least this semester, fall of 25, will include hurricanes on test number 2, because we did that last week before we started minerals. What else? No clue. Another month. Yeah, it's not anytime soon. End of October, I'd say. Thereabouts. I tend to put 3 to 4 PowerPoints on a test, so I'm guessing what comes next. Igneous. So we're going to do igneous and volcanoes before that, which is going to be kind of a thick test, but yeah. Maybe not volcanoes, because there's also intro to rocks, too. So not for a couple weeks. Just keep it simple as we can at this point. All right, any other questions? Other questions? Okay, guys. Let me stop the recorder here.